Our next topic is determining the pH of salt solutions. So salts is just another name for ionic compounds. Remember when we did the types of solid in class, we have both molecular solids as well as ionic. So something like NaF is an ionic solid, and that's going to dictate what happens to it in water. Ionic solids dissociate into their ions. So something like NaF is ionic, we can tell because it has that metal cation, Na+, and then a fluoride ion, F-. Similarly, NH4NO3. Even though everything in that is a nonmetal, you should recognize your polyatomic ions in that. That contains the polyatomic ions NO3. So you should recognize NO3- there as one of your polyatomic ions, and the other polyatomic ion there is NH4+. So even though there's no metals there, it is still an ionic compound by recognizing those polyatomic ions. Similarly, KCl, that one is a little bit easier since it's just a metal and a nonmetal, so that's a K+ cation and a Cl- anion. Now contrast that to our molecular solids, where those are all nonmetals but with no ions really. So HCOOH is just a covalently bonded compound, and that goes into solution as just the neutral molecule. Always the first thing we need to do when we're thinking about a solution and its pH is to first think about whether it's ionic and dissociates or molecular and stays together in solution. The other contrast then is these molecular solids are what's in our table. So these things we're going to be able to find in our table of Ka or Kb. On the other hand, these ionic compounds aren't generally, these ions aren't typically in our table, so here we need to look for the sort of neutral conjugate when we try to figure out the K for that particular acid or base. Preamble out of the way, now let's actually figure out whether these are acidic, basic, or neutral salts. So NaF is ionic, and so the first thing we need to do is think about the ions that are formed when it goes into solution. Na+ plus F-. Now we think about the acid-base properties of each of those ions. So Na+ is not acidic in any way. We can ignore it. It doesn't have any effect on the pH. It's one of those group 1 cations. What about F-? Well, anions have a tendency to be bases, so we should be suspicious that this might be a base, because if we think about it, F- has all those lone pairs and a negative formal charge. Hey, we could make a bond to an H+ to make the conjugate acid. So that's what we do need to think about. We need to say, okay, we'll think about the conjugate acid. If we are suspicious F- is a base, let's think about the conjugate acid, which is equal to HF. So based on what HF is, we can categorize F-. So HF, if we think about that one, it is in fact a weak acid. In our data tables, it has a Ka. Ka less than 1, it's a weak acid. Therefore, since HF is a weak acid, that makes F- a weak base. And therefore, this entire solution is basic, and the thing that's going to happen in an NaF solution is F- will act as a weak base, make a little bit of OH-, and that's going to be what affects the pH. So we'll have something like F- plus H2O liquid goes to, again, the conjugate acid, HF, plus OH-. For this type of reaction, what are we going to have? This will be a Kb reaction since it's F- acting as a base, and we can find Kb using Ka for HF, and this relationship 10 to the minus 14 is equal to Ka times Kb. So that's the idea. The extra steps involved here are just all of this sort of chemistry background information of knowing that it's ionic, looking at the properties. Oh yeah, F- conjugate acid is HF. looking up HF in the data table to verify that it's a weak acid. The conjugate of a weak acid is a weak base. And then this problem is the exact same way we'd solve in any other weak base. Just, figure out its concentration, solve for X, ice table. The new part of it is just making sure you can do this analysis properly. What about the next one? NH4NO3 dissociates into the ions NH4 plus and NO3 minus in solution. So let's think about the acid-base properties of each of those. NH4 plus, if we look at that, that is a nitrogen with a positive charge on it. That we should be suspicious that it should be an acid. So is this thing an acid? It's not a strong acid, just our 6 that we've memorized, but that does look a lot like an acid. We won't generally find that in our data tables of weak acids. So again, the same way for F minus, we thought about the properties of the conjugate acid. If we're suspicious that this ion is going to be an acid, let's look at its conjugate base, which will be neutral. The conjugate base here is going to be NH3. And if we look it up, that is in our table. We can look up the Kb for this, which means it is in fact a weak base. And because NH3 is a weak base, that means that NH4 plus is going to be a weak acid. Same idea as before, where we can use that K 10 to the minus 14 is equal to Ka Kb. Now from our data table, we're going to know the value of Kb. That's going to be known. So we'll solve for Ka by dividing both sides by Kb, and that will let us get the Ka for this weak acid. What about the other ion, NO3 minus? Well, NO3 minus, it's a negative ion, so we should suspect that it might be a base. But if we recognize our strong acids, we should recognize that the conjugate acid here is going to be HNO3. Add a proton and increase the charge by 1. HNO3 is a strong acid, though, which makes NO3 minus an ineffective base. And so this ion does not affect the pH in any way. So by memorizing your strong acids, you also sort of by default have memorized the list of ineffective bases. NO3 minus is one of those 5 common key ions that doesn't affect pH. And so we can ignore it when we're thinking about the pH of a solution. This doesn't have an effect in the same way that Na plus had no effect on the solution. So the final way we'll calculate the pH of this solution is by taking NH4 plus. It acts as a weak acid, so it reacts with water and makes a little bit of H3O plus and the conjugate base, NH3. And again, this is a Ka reaction. We get Ka as shown here. Our last example is KCl. That has a potassium and a chloride ion. So the two ions are K plus and Cl minus. K plus is one of those group 1 cations, so it doesn't have any effect on the pH. Cl minus is an anion. We should suspect that it might be a base, but if we think about its conjugate acid is HCl, which is a strong acid, which makes Cl minus an ineffective base. And so similarly, just like our NO3 minus was an ineffective base, Cl minus is an ineffective base for that exact same reason. So all of that memorization of the strong acids, which gives you the ineffective bases, and again the strong bases, which gives you those cations that are ineffective acids, really pays off here. Now again, since neither the cation or the anion affects the pH, this is just a neutral salt with a pH of 7. So again, knowing this key table, the conjugate base of a strong acid is effective, the conjugate base of a weak acid is a weak base, and vice versa. And this strong base, ineffective acid, strong base relationship down here is essential to dealing with salts. Now let's see how we can actually calculate the pH of a salt. So here is 0.1 molar ammonium chloride. Try to figure out how you can calculate the pH. First step here is that this is in fact a salt. The ions are ammonium and chloride, so this dissociates in water to form NH4 plus ions and Cl minus ions. Then we think about the acid-base properties of each of these. NH4 plus has that nitrogen with a positive charge, which is definitely characteristic of potentially being a sort of acid, a weak acid since it's not one of our 6 strong acids. Again, that same check, think about the conjugate base. The conjugate base is equal to NH3, which is in our table of weak bases. So this NH3Kb tells us that NH4 plus is in fact a weak acid. Cl minus is negative. We should suspect that it's a base, but just as on the previous slide, its conjugate acid is HCl, which is a strong acid, and so therefore it's an ineffective base, and Cl minus doesn't affect the pH of the solution at all. So we're left with just NH4 plus being the important ion. NH4 plus is a weak acid. It reacts with water to form a little bit of H3O plus and the conjugate base NH3, just as we showed on the last slide. Now we can go through and do our ice table and everything like that. Since it was 0.1 molar NH4Cl, that means when that breaks up, it makes 1 NH4 plus and 1 Cl minus ion in solution. So our initial concentration of NH4 plus in our ice table will be 0.1 molar. So that's our problem setup. Again, see if you can do this using the Kb from the table, and then I'll show you the solution. From the previous slide, we had the reaction, but we do need the K equals Q. Since NH4 plus is a weak acid, this is a Ka equilibrium that we're thinking about. And so this is Ka is equal to H3O plus NH3 over NH4 plus is the K equals Q expression. We do need a value for Ka, however, so we may as well do that now. That comes out of the fact that 10 to the minus 14 is equal to Ka times Kb. So Kb for NH3 was given to us from our data table or the previous slide, and that then means we can solve by dividing both sides by Kb. That gives us 5.6 times 10 to the minus 10. That finishes out step 0. Now step 1, our ice table. We had on the previous slide 0.1 molar was our initial value of NH4 plus. H2O is a pure liquid, and we started with none of the products. Since we started with 0 products, the reaction has to run to the right towards products, so we'll make a little bit of those to get to equilibrium. Then we'll use up a little bit of NH4 plus. All the coefficients are 1 here. Equilibrium, 0.1 minus x, x. And our final, that's the end of our ice table. Now we can plug into K equals Q and choose a method to solve. So we go 5.6 times 10 to the minus 10 is equal to x over 0.1 minus x. That's plugging into K equals Q. Now let's choose our method. K is very, very small. So expect the equilibrium to lie all the way back to the left towards reactants. X should be very small, and we should be very safe to choose that small x approximation method. So making that approximation, 0.1 minus x will basically be equal to 0.1. Simplifies our ice table, or simplifies our K equals Q to this. Multiply both sides by 0.1. And then take the square root. We get our final value of x here, 7.48 times 10 to the minus 6. That is much less than sort of the 5% of the thing we ignored. So very safe to make this approximation. And then again, make sure we actually finish the problem. The goal here is to get the pH, so we can do that by plugging back into the equilibrium row. H3O plus is equal to x. And then we can go from there and say negative log of H3O plus is our pH. My final answer there is 5.13. That makes sense. This is a very, very, very weak acid, so even though we have a reasonable concentration, the pH is only very slightly acidic here. Again, just because of how weak the acid is, so equilibrium is lying really, really far to the left. and x is really, really, really tiny. So here are a bunch of practice problems. We'll often take time in class to work on these problems. I'd encourage you to do a lot of these type of problems because now that we have so many different types of solutions, it can be easy to mix things up a little bit if you're not really sharp about identifying strong acids, strong bases, weak acids, ionic compounds, etc. So definitely, work through the practice problems and look at the solutions. Here's one more of these. This is another one where we're not going to actually do the actual problem, but just sort of set up the problem or, talk about how we would solve these. So take a minute to try these. Okay, once we have this now, again, the key thing we need to do is categorize the solution. Is this molecular? Is it ionic? Is it a strong acid, a strong base, a weak acid, a weak base? For the first one, HI, that's one of our best cases there. That's one of your memorized list of strong acids. So you memorize that it's a strong acid, and then we just go through and get the answer. Because it's a strong acid, it dissociates completely. And so HI reacts quantitatively with H2O to make H3O plus and I minus. And so a 0.1 molar solution of HI is going to have 0.1 molar concentration of H3O plus. So H3O plus is equal to 0.10 molar. And we can get the pH directly from the definition there. It turns out to be exactly 1.00 here. Just, again, using stoichiometry, no need to introduce any sort of ice table or anything because it's just a strong acid. For B, 0.1 molar NH3, you should recognize that that's a molecular type of compound. It's not ionic. And so since it's molecular, we can just sort of look it up right in our data tables. It's not a strong acid. It's not a strong base. It doesn't meet that definition. It is a nitrogen-containing compound with a lone pair, which makes it likely to be a base. We can look up ammonia in our table of bases, and we do in fact find Kb is equal to 1.8 times 10 to the minus 5. So it's a weak base. We have to make an ice table, solve for x, use the OH minus from the Kb reaction to get POH, and then get pH from there. That's going to be how we would solve that. Next, for a 0.1 molar solution of NaCN, when you look at NaCN, the first thing that should sort of pop out at you is the presence of that sodium ion. So Na is a metal. That means that in this part of the class, we definitely have an ionic compound, which means we need to dissociate into its ions first. Na is in group 1, so that's going to be an Na plus ion plus a Cn minus anion. Na plus is one of those ineffective acids that doesn't affect pH, but what about Cn minus? Cn minus is negatively charged. We should be suspicious that this is some sort of weak base because that negative charge could pick up a proton and become a neutral molecule. Again, to verify that, we'll think about the conjugate acid, which is HCN, not HNC, HCN. And HCN does, in fact, if we look at our data tables, have a Ka in our data table, which verifies that this is a weak acid. And therefore, Cn minus is, in fact, a weak base. We can get Kb using Kw over Ka, set up the Kb reaction, and solve it the same way as for NH3, but just starting from Cn minus acting as our base, rather than the neutral NH3 acting as the base. Because acid-base chemistry is so important in your body chemistry and all of its applications, it's important to be able to control the pH. The way the pH can be controlled is through a buffer solution. So first, what is a buffer? It's a solution that can withstand the addition of H plus or H3O plus or OH minus with a minimal change in pH. So for example, your blood pH has to be maintained between 7.35 and 7.45. If it gets much outside of that range, very deleterious to human health. Now, this is not easy to do because your breathing rate affects the concentration of CO2 and also the blood pH because of this equilibrium. CO2 gas reacts with H2O liquid to make H2CO3. So take a minute to think about how hyperventilating would affect the H2CO3 concentration and therefore also the pH. Okay, so hyperventilating is expelling a lot of CO2. That means that our CO2 concentration is going to go down. That's our Le Chatelier stress. When we decrease CO2, Le Chatelier says we have to shift to oppose the stress, and we'll shift left to make more CO2 or more reactants. When we shift left, that's going to cause the amount of H2CO3 to go down. Shift left towards reactants means we use up our products. A decrease in H2CO3 means we're going to have less less acid. H2CO3, carbonic acid is a weak acid, less acid, which means a less acidic or more basic pH. And this does, in fact, put you at risk of alkalosis, a too alkaline or too basic pH. This is the name of that affliction, respiratory alkalosis, when your pH goes too high. The way your body prevents this from happening, except in extreme cases, is by containing a buffer. In this case, this is actually the same substance that's acting as the buffer. So H2CO3 and HCO3 minus, there's significant amounts of both of those ions in your blood. And what that does is it prevents any immediate changes in H2CO3 or HCO3 minus from causing a large change in the pH. So these two components of the buffer sort of act as a sponge that can sop up or release H3O plus ions as needed. The definition in general here is a buffer is a weak acid and the weak acid's conjugate base. So weak acid, weak base, conjugate pair is the definition of a buffer that we need to be able to apply. Using that definition of a buffer, take a second to think about which of these solutions are buffer systems. Okay, so we need weak acid, weak base, conjugate pair. For KF-HF, I'll pick the one that's a molecular thing first, just because then I don't need to break something into ions to start out with. HF is just a neutral molecule. It's not one of our strong acids. If you look it up in your table, it has a Ka, and it is in fact a weak acid. So since HF is a weak acid, if I can make a solution that contains HF plus its conjugate base, which is equal to F minus, then I have a buffer. If I look at KF, KF is K plus ion plus F minus anions, and so this is in fact a buffer solution because I have both HF and its conjugate base F minus in solution. And this is a weak acid and a weak base conjugate pair. What about KBr, HBr? Well, HBr is one of our strong acids, and that by definition then does not meet our definition of a buffer. We need a weak acid, weak base conjugate pair. A strong acid, it doesn't work, so not a buffer. What about our next one? Na2CO3, NaHCO3. Both of these are ionic, so I don't know that one is easier to start with than the other. I'll pick Na2CO3 to first start with. We see that it has those metal ions, so when this goes into solution, we get two Na plus ions plus a CO3 2 minus anion. Again, because there's 2 plus, we know this is CO3 2 minus. It's also one of our polyatomic ions to sort of know and recognize. CO3 2 minus has a negative charge, and those oxygens with negative charges on them. So again, this looks sort of like a base because it could pick up a proton, and that's what a base does. It can accept protons. So what is its conjugate acid? Its conjugate acid is equal to HCO3 minus. Did we put HCO3 minus in solution? Well, yes, because our other compound here is an Na ion along with an HCO3 minus ion. So this second component here does contain HCO3 minus. That is the weak acid half of the buffer system. So we have HCO3 minus, a weak acid, and CO3 2 minus, a weak base. To verify this, because this is a polyprotic acid, you actually have to go to that table of polyprotic acids and look for H2CO3 in that table. H2CO3 is in that table with a Ka1 and a Ka2. The acid is HCO3 minus, so it's really the Ka2 that would govern this sort of equilibrium system. Just highlighting the relevant region from that polyprotic acid dissociation table, Ka2 is the K for HCO3 minus, which does verify that it is a weak acid, and so therefore CO3 2 minus is a conjugate, is a weak base. Next, let's look at what happens when we actually try to, affect our buffer. So an unbuffered solution here of just sort of water with a little bit of acid in it to make it pH of 4.74. When we add a little bit of concentrated acid, the pH changes by this huge amount, 4.74 to 3. When we have a buffered solution here, now the pH only changes by 0.01. So that's the whole point of a buffer. As long as some of that weak acid, weak base sort of conjugate pair is available, it can resist changes in pH. Eventually, we will overcome the capacity of the buffer. And the more concentrated the buffer, the greater its ability to resist change, because it's sort of like having a larger sponge to sop up additional H plus or OH minus ions. We can define a buffer capacity here as well, the amount of acid, strong acid or base that's needed to change the pH by 1 pH unit. That's sort of a sign of our buffer completely failing once we change by 1 pH unit. When working with buffers, this is such a common situation that it's useful to have an equation that handles that situation. Now, you could just apply normal equilibrium principles, but since we deal with this so often, we can rearrange the Ka equation and get this nice result. We rearrange the Ka equation and get this result that pH is equal to negative log Ka. This is written as minus log Ha over A minus. But the next thing that we do is we define a pKa, which is just like any other p of something. It's negative log of that thing. So pKa is negative log of Ka. And what's the next thing? I guess we flip this here just to get it in the form of base over acid so we don't have this extra minus sign lurking around. And now we have this equation that will let us get the pH of any buffer solution. If I know the amounts of acid and base, and I know the pKa, which I just get from the Ka of the weak acid in the buffer, I can now get the pH without having to do an ice table or any other types of calculations. So the first sample, the pKa of carbonic acid, given its Ka. Just plugging into the formula, pKa is negative log of Ka, so negative log 4.3 times 10 to the minus 7. When I do that, I get 6.37. And that's very common that the pKa will be in that range of sort of 0 to 14, just like whereas H plus concentrations are in that very small number range, pHs are often 0 to 14. pKas are also often in that 0 to 14 range on the same sort of scale as pH. Okay, here's our first example calculation. Calculate the pH of a solution made from 0.3 molar formic acid and 0.52 molar potassium formate. Here's the Ka of formic acid. You can do that either using the Henderson-Hasselbalch equation that we defined on the previous couple of slides, or using a normal ice table approach. I'll show both of those on the coming slides. Okay, first the ice table approach. So first thing we always need to do is recognize that it is a buffer. So formic acid is a weak acid. HCOOK contains the conjugate base, HCOO minus, so it is in fact a buffer. Whenever we're thinking about a buffer, we always just write the Ka reaction. In theory, you could write the Kb reaction too, but it's always just easier to write the Ka here. So this is the equilibrium. HCOOH reacts with water to form HCO plus and HCOO minus. K is equal to Q, shown here as well. Now, the next piece of this here is if we're using this approach, we'd fill out our ice table. So in this case, we would have 0.3 molar HCOOH. That's just the given formic acid, 0.3 molar. We would also, though, have, since we put 0.52 molar potassium formate in solution, we have 0.52 molar HCOO minus on our ice table. So as opposed to this case where we started out with only reactants, now we have some products present initially too. When we think about the method we would want to use to solve, in general, since Ka is small, this reaction lies further to the left. In this case, because of the added products, if we think about a Le Chatelier argument, we added, compared to just dissolving the weak acid in water, we added a bunch of the conjugate base here, HCO3, sorry, HCOO minus. When we did that, that shifted equilibrium back even further to the left, which makes X even smaller than it would be otherwise. So that means that we'll definitely be able to approximate. We don't run any risk of the approximation failing. Again, because of this Le Chatelier effect of adding the common ion, causing a shift back to the left. When we do that, we can approximate. In this case, if we're approximating, we expect X to be small, so 0.52 plus X is about 0.52, 0.3 minus X is about 0.3, and we get to our solution very, very quickly then. Just take the Ka times 0.3 divided by 0.52, and we get our value of X here. 1.04 times 10 to the minus 4 is X. Then we plug in, yes, that's much less than 0.3 molar. No real need to check that for a buffer. If it's a buffer, the approximation always works. And then the pH negative log of H3O plus gives us 3.98. To our understanding of the pH of a buffer, we need a little bit more information to do that, but this does in fact make sense. We'll see later that the pH of a buffer should be pretty close to its pKa. So if we calculated the pKa of HCOOH, the pH of the buffer needs to be pretty close to that. This is just drawing out that thing we mentioned on the previous slide, the common ion effect. So what the common ion effect is referring to the fact that how is H3O plus going to change when we add potassium formate? So let's say we establish an equilibrium with just the weak acid. Now we add potassium formate. The stress is increased HCOO minus. That causes a shift back to the left. When we shift left, what happens? Well, when we shift left, that's going to cause a little bit of the H3O minus to be used up and a little bit of the COOH to be reformed. So this is called the common ion effect, and it's always has the same form, that we shift back towards the reactants and have less dissociation of the acid. So adding that common ion suppresses the dissociation of the acid. This effect will come up later when we're dealing with solubility products as well. The other approach that is a really good approach to solve buffer pH calculations is just to plug into the Henderson-Hasselbalch equation. So in this case, we are given the Ka, so we can calculate the pKa from the Ka. So from pKa, we plug in negative log of Ka. So the pKa was 3.74. We use the Henderson-Hasselbalch equation. A minus is the conjugate base. That's 0.52 molar. Ha is the conjugate acid, 0.3 molar. We don't need to worry about X's there. Just plug in, and we get our answer. So that's usually probably what people find the easiest way to get the pH of a buffer. Recognize that it's a buffer, and then just apply the Henderson-Hasselbalch equation to get the pH. Here on the bottom of the slide, there's really no reason to ever plug this into solver or quadratic equation or anything like that. Henderson-Hasselbalch works great as long as you recognize that you have a buffer. Our next idea here is how we would make a buffer solution. So in general, the thing we want to do is find a pair who has a pKa pretty close to the pH that we want to maintain. Then we can figure out how much of each we want to put in the solution, prepare the solution, and adjust the pH to get to the appropriate value. That's something that if you take higher level chemistry, biochemistry, or upper level biology classes, you'll have to prepare and use buffers because they're so important in dealing with cells, proteins, any other sort of analysis. Okay, here's our next example. Calculate the pH of a solution containing 0.3 molar NH3 and 0.36 molar NH4Cl. The easiest way to do this is using the Henderson-Hasselbalch equation. So we'll plug in there. pH is pKa plus log. You can view it as A minus over HA, or just sort of base over acid. So pH is equal to, pKa is defined as negative log of Ka off of the equation sheet, plus log. Again, NH3 is a weak base, and NH4 plus is my weak acid. So that means that when I plug in here, I'll need to put in 0.36, that's the acid. So plug that in. And 0.3 molar then is the base. The Ka is what goes into the pKa equation, so I'll plug that in as well. Now that we have the Ka plugged in, we just solve. Do that, we get a pH of 9.18. The pKa happened to be 9.25, and so then this term here, we have a little bit more acid than base, so that makes the pH a little bit more acidic, or a little bit lower pH than the pKa, which all checks out. More acid is equal to a more acidic solution with a lower pH. Okay, the final couple of slides here. This just shows a picture of what happens when we are acting as a buffer. If we're at this point right here where a buffer has equal amounts of acid and conjugate base, adding a little bit of H0 plus or adding a little bit of OH minus, the H0 plus just converts a little bit of the conjugate base to the conjugate acid. And because this is the formula for H0 plus, this ratio might change from like 1.00 to 1.05 or something like that, and we get a very small change in H0 plus because this ratio only changes a little bit. As soon as we get to the point where the ratio is starting to get pretty extreme here, maybe we're over here where this is 9 and this is 1. Now when we add a little bit here, this ratio starts to change by a large amount, and H0 plus starts to change by a large amount. So as soon as we, in this case, say start using up the amount of the acid here, we'll start to lose the buffering capacity of this solution. So this is what we see here. We have that best buffering point where pH is equal to pKa, the H0 plus is equal to the Ka, and the concentration of the weak acid is equal to the concentration of its conjugate base. If we're a little bit more acidic than that, we have a little bit more of the acid. A little bit more basic, we have a little bit more of the conjugate base. Okay, using that, take a minute to think about how you can prepare a buffer at a pH of 4.00. Which acid and which salt will work to make the best buffer possible in this situation. Okay, so the best buffer we want, based on the previous slide, we want the pKa as close to 4.00 as possible, because if the pKa is exactly 4, then we'll be at that best buffering point for the system. Now, rather than calculating pKa equal to 4 and having to calculate the pKa of a bunch of different buffer systems, let's turn that into a Ka. So if I have pKa equal to 4 is equal to negative log of Ka, I can undo that to solve for the Ka. To solve for Ka, I'll take negative 4 is equal to log of Ka, and then take 10 to the power of both sides to undo the logarithm. When I do that, I get 10 to the minus 4 is equal to Ka. That's the Ka that I'm looking for. Let's see what I have of my provided buffers here. So HCl, NaCl, that won't be a buffer because we've got a strong acid. HF, NaF is a buffer. The weak acid in that buffer is HF, so that's a possibility. That has a Ka of 7.2 times 10 to the minus 4. That's not bad. That's pretty close to what I'm looking for. I'm a factor of 7 too big, but not terrible. HF and HCl, this is a weak acid and a strong acid, so that's not a valid buffer. What about some of these other ones here? HC3H5O3, NaC3H5O3. That is in fact a buffer. It's got a weak acid here, and the conjugate base, this happens to be lactic acid. bane of any endurance athlete. So lactic acid here, and this is the sodium lactate. This is the conjugate base. If we look at this, then the pKa is 1.38 times 10 to the minus 4. That's a great match and definitely the best case here. E is way off. That's is a buffer, but we can see its Ka is 10 to the minus 2, not close at all. So therefore D is the best choice here. A lactic acid and sodium lactate buffer will work best at a pH of 4.